I want to spend a little bit of time talking about solution stoichiometry. The stoichiometry that you're probably used to doing or have more experience with is just when you're going from grams to grams. But we need to talk about what happens when your balanced equation involves a solution. Okay, because a solution, as you know, is a homogeneous mixture, which means it has a solid solute, typically, not always, but most of the time it has a solid solute dissolved in usually water, okay? And in the balanced equation, you'll see an AQ next to substances that are solutions to let you know that that is an aqueous solution. So the AQ signifies that it's dissolved in water. And that requires you to approach the stoichiometry a little bit differently. Solutions are typically in chemistry measured in a unit referred to as molarity. And molarity is moles of solute divided by liters of solution. Because the solute is typically a solid, usually the volume of the solute is pretty small compared to the volume of the water, which is your typical solvent, which means that for all intents and purposes, the volume of your solution is typically the volume of your solvent, which is water, okay? And molarity is just, again, moles of solute divided by liters of solution. An example that we will look into in more depth would be acid-base reactions, which typically involve solutions of acids and bases. First of all, acids are very, very corrosive. Even when you are working with a concentrated acid, you are still working with a solution of that acid, never in the pure substance, or never in the pure form, okay? So even the most concentrated acid, so like sulfuric acid, you can get as an 18 molar solution. That's still, like, what that means is you have 18 moles of sulfuric acid dissolved in every liter of water, okay? So what I want to do is I just want to show you how to approach stoichiometry problems using molarity information, okay? In case this is new to you. So keep in mind a couple of things that I want to point out to you is that, first of all, keep in mind that the key to stoichiometry is the mole ratio, okay? So when we're using this molarity equation up here, think about the fact that molarity is moles per liter, which means it's going to help us get to moles, which we need for the mole ratio. Secondly, the other thing I want to point out before we get started is sometimes people have a hard time understanding how to set up their fence to do this, which, by the way, that's what I call dimensional analysis, is a fence, because that's what it looks like to me. People have a hard time understanding, like, which substance do I start with, which substance do I end with, because there's a lot of numbers in these problems, and it gets somewhat confusing. So my advice to you is to always figure out, like, which substance are they asking you to find information about. So in this case, it says what volume of NaOH. Okay, so that tells me NaOH is the substance I need to be finishing with, which means I must start with HCl. Okay, so you're going to take your information of HCl and using a fence or dimensional analysis, you're going to convert it into information about NaOH. All right. Okay. So let's talk about how to do that. So we have two pieces of information about HCl. All right. We have the 50 milliliters, which is volume, and we have the molarity. Well, keep in mind, okay, that molarity, so when you have 0.200 molar HCl, what that really means is you have 0.200 moles of HCl per 1 liter of H2O, or 1 liter of solution would probably be a better way of saying it. So I'm going to change it to solution. Okay. And the other thing I would keep in mind, because while molarity, the equation itself functions in liters, that it is very rare that we are measuring amounts in liters. Like usually we're working with much smaller quantities, so we're using milliliters. So I would just extend that a little further and say that means there's 0.200 moles of HCl for every 1,000 milliliters of solution. Okay? So this information right here with molarity has now been turned into essentially what's a conversion factor that we can use in our fence, okay? So what I would do then, and I'm going to switch colors, is I'm going to start, like, look at how this is set up. You have moles on top, milliliters on the bottom. Well, I need moles to get to my mole ratio, so I want to get rid of milliliters. So I want to start with milliliters. So I'm going to start with my 50.0 milliliters of HCl, right? And what I'm going to do here is I'm going to use my molarity to continue to get rid of the milliliters that we have. Okay, so what I'm going to do here is I'm going to put 0.200 moles up top of HCl and 1,000 milliliters of solution on the bottom. And that's my HCl solution. So you can see I just got rid of milliliters. And now what I have is moles of HCl, which is useful because I can use those moles and the balanced equation to convert to NaOH. Remember, the key step, again, is your mole ratio. That's like your magic ratio where you can switch from one substance to the other. So if you look at the balanced equation up here, it's a 1-to-1 ratio. So 1 mole of HCl for every 1 mole of NaOH. Okay? And then your moles cancels out. Then the last step that you want to do is, so, now we have moles of NaOH, but we are asked to find volume, which we can do because we have our molarity information. Okay? And we can still use that in the fence, similarly to how we did the HCl. We're just going to use it upside down this time. So we're going to say that we have 0.130 moles of NaOH. That's going to go on the bottom because that's where it needs to cancel out for every 1,000 milliliters. Okay? Which then, if you plug that into your calculator and you get an answer, then you should find out that you get around 76.9 milliliters of NaOH, okay? And you do, just so you know, you want to have 3 sig digs in your answer because the number you started with had 3 sig digs. 50.0 is 3. And so that would be how you would do this type of problem.